Okay. Last lecture, you remember that what we did is we started with the Clausius-Clapeyron equation, right? That pressure is equal to this E. By the way, E, I want to point out, and maybe I'll write it out one time. E is just a number, okay? It's 2.71, some more digits. Okay, I don't know all the digits to it. Your calculator does. But so E to raised to the heat of vaporization over RT, right? We had that. Plus, there was, I'm sorry, I forgot our beta. So it was beta, this number beta, some number beta, which is empirically derived, times E raised to that. And then we did some algebra to that. And we ended up with the logarithm, natural logarithm of the pressure is equal to negative heat of vaporization over R times 1 over T plus the natural logarithm of beta. Okay, I'm not going to go over that algebra again right now. But so we did that, and the point of that was that you could take a set of data like what I have up here, and you could graph it and get a straight line, because this is the form of a straight line equation. Y is equal to mx plus b. Okay, just like that. So that's useful. More useful for us, because we're not going to hand graph in class and we're not going to have computers for quizzes or tests, is we would do more algebra. Really, we subtract this equation under one set of conditions from another equation under a different set of conditions. Okay, just subtract them, and what we got from that was the 2-point version of the Clausius-Clapeyron equation, which says the logarithm of some pressure over some other pressure, two pressures, pressure 1, pressure 2, is going to be equal to the heat of vaporization over R times 1 over the temperature that goes with the first pressure minus the temperature that goes with the second pressure. Okay, and this is the equation that we're going to, you might have to use on a quiz or test or something, like next week's quiz. So I want to work a problem using this. And I want to work a problem where we have to solve for this. And the reason why I'm going to work it, the reason why I derived these, and part of it was that I wanted you to see that we just do algebra to get all these things, right? The other thing was I wanted you to get some practice looking at what we're doing for various things in algebra, specifically with the logs, okay? My first hope would be that you would have looked at that lecture, I would have derived stuff, and it would have been so easy for you that you were bored, okay? But I know a lot of people have not had a lot of log sets. I know that's barely anybody in the class. And then hopefully that you saw some of the stuff we did with algebra. We're going to work this problem today, but big part of working it is the algebra and using the logs. How do we do that correctly in terms of working this problem? So what we're going to do is I'm going to go ahead and grab data from the end of this table up here, and I'm going to make up a problem. So we're going to say that we have a pressure 1 that's equal to 228.77 torr. That's our pressure 1. We're going to say our temperature 1 that goes with it is 300.0 Kelvin. Okay. The new pressure, we don't know. Okay, because I want to solve for that. I want to solve for something on the bottom. And then our new temperature, I'll give you the same temperature I did with the previous class. So 450 Kelvin. And then our heat of vaporization, I worked with this with some students yesterday, so I know that it's 13.7 kilojoules per mole. Okay? And then finally, on the top of my quiz or wherever, I would look up my ideal gas constant. The one I want to use here is the one that has joules in it. So 13.14 joules per mole Kelvin. Okay? The way these problems work is you have 1, 2, 3, 4, 5 things here in this equation, right? That aren't constants. So heat of vaporization is going to be different for each compound. The ideal gas constant is just a constant. And so what we're going to do is we're going to take, we've got 1, 2, 3, 4, 5 things. You're going to be given 4 of those things or a way to calculate 4 of those things, and you need to solve for the 5th one. Okay? I was hoping this would be better. Okay, so let's go ahead and do that. We've got all our pieces over here. All right, so the first thing I want to do is I want to just put all my numbers in. I'm going to put all my numbers in, and hopefully I can make some of them into, combine some of them so I don't have to worry about it so much. So if we go ahead and write this out, you maybe wrote those down, you maybe didn't. I got them memorized at this point. So the logarithm of our first pressure was 228.77 torr, right? Our second pressure, that's what we're solving for. Our heat of vaporization was 13.7 kilojoules per mole. Our R is 8.314 joules per mole Kelvin. Okay, and our temperature 1 was 300 Kelvin. And we're subtracting from that, our temperature 2 is 450 Kelvin. Okay, great, but I do have a problem here. What's my problem?
You have to separate the natural log out into this.
Okay, we're going to need to deal with the natural log, so we can do that. But before that, there's a problem with what I got. Yeah, I've got a kilojoule. This is in kilojoules and this is joules, so they won't cancel. So I need to make them match. Which one do you want me to change? We're going to change the kilojoules to joules. Okay, let's do that. So we need to put something else in there. So I have 13.7 kilojoules per mole, and I want to change it to joules. How many joules in a kilojoule? 1,000. And what? So what do I? Where does the joules go? On top. So what do I write on top? 1,000 joules.
Sorry.
That's good. And I asked all of those because sometimes people don't pull the number along with the units, right? There's 1,000 joules in a kilojoule. 1,000 is stuck to the joules. So that's equal to a kilojoule here. These two things cancel, right? And that's gonna give me 13,700 joules per mole, right? I'm gonna go over here and I'm gonna erase this and fix it by putting in negative 13,700 joules per mole. All right, now I'm happy because this joules cancels with this joules. Joules on the top, joules on the top and the bottom. Moles on the bottom on the top, moles on the bottom on the bottom. Okay, those cancel. And then here's the one that's kind of confusing. Over here I've got my kelvins, right? I'm going to subtract those, so it's going to give me a Kelvin, right? If I subtract 1 over Kelvin from 1 over Kelvin, I get 1 over Kelvin for my units. And I have Kelvin on the top, on the bottom, on the right. And I have Kelvin on the bottom, on the left here. So these will cancel. All my units have canceled. And so I'm left with torr as units over here, right? My answer is going to be in torr. Great. That's what I'm looking for. I'm looking for units of pressure. So far, so good. Questions on anything I've done so far? All right, so now I'm going to pick up my calculator, and you're going to have to learn how to use your calculator in terms of, and I'm happy to help you with that, by the way. But you're gonna need to learn how to use your calculator to do these things efficiently. So I've got a little 1 over x key in my computer, or my calculator. I'm going to use that here. So I've got 300. I'm going to put 300 in my calculator. I'm going to hit 1 over x, and then I'm going to subtract from that for 450 1 over x, and then I'm going to hit equals. And I'm going to just leave that number in my calculator so I don't have to write this down. But I am going to write this down in case you want to check what you did. So that's what I got out of that. 0.00111111. Okay? And now I'm going to multiply it times that 13,700. And I'm going to divide it by 8.314. And I got the same answer I did last time. So I think all is right with the world. When I get done with all of that, what I've got is the natural logarithm is 228.77 torr over P2 is equal to, I've got negative 1.8, we'll say 3, okay? With no units, because I canceled them all. Everybody okay with that? All right. So now the next thing I want to do is I want to get rid of that natural logarithm. Okay, and the way I do that is I'm going to take e to both sides. All right, I'm going to cross this out real quick. Remember, this e thing is funny and it ends up being confusing because it's mathematicians' favorite number. They like it even more than pi, I think, even though they have pi day. I don't know why they don't have e day. Guess they can't throw e's at you. But remember that we're just taking 2.71 and we're raising 2.7 to the logarithm of 228 over P2, and we're raising 2.71 to negative 1.83. Yes? It is E.
Oh, okay.
I'm just trying to, this E thing is kind of abstract. I'm trying to, we're raising E. We're not multiplying E times stuff, right? Yes.
Is it constant to
The E, yes. E is always the same number. Okay? All right, so if I raise the logarithm-based E to the logarithm-based E of something, that just becomes that something. Okay? I don't want to say cancel. But I end up with this over on this side. On the other side, all right, we spent some time working on this in our calculators in the last class. Everybody's calculator is going to act a little bit differently. So I have an E key. For me, what I would do is I would put in 1.83 and make it negative. And then I've got my E to the X key. So then I press my E to the X key. You might have to press the E first and then put in negative 1.83. But if you've done it correctly, what you should get out is 0.160, let's say 4. Okay. I'll pause for a second. Anybody have questions on that? I don't want to go over everybody's calculator specifically, but I'm happy to take a couple rounds here because I know it's difficult. So for my calculator, I put in 1.8, and then I have a little plus minus key, and I hit the plus minus key. Okay, and then I hit the E to the X key. Did that go for you? No. You think you figured it out? Yeah. Good. Okay. If you don't have it figured out, come up to me after class and show me your calculator, and we'll figure it out. Okay. So now I've got P2, which I'm solving for, on the bottom over on the left. How do I get rid of that, or how do I get it on the right? I'm going to cross multiply, or I'm going to multiply both sides times P2. Okay, cross multiplying is kind of the same thing, but I'm going to multiply both sides times P2. I like that, saying it that way, because we're following our rule in algebra where we can do anything to one side of the equation as long as we do it to the other side. Okay, that's our rule that always happens. So those P2s are going to cancel, and now I'm left with 228.77 torr is equal to 0.1604 times P2. All right, and then to solve for P2, I'm just going to divide both sides by 0.1604. All right, and so what I get out of that is I get 1426 torr is equal to P2. Okay. You may have gotten slightly different things if you were rounding slightly differently as you went through. Okay. So you want to show your work when you do these sorts of things, and I can look and just see if the rounding is slightly different. Like I got a different answer last time because I did 1.8 instead of 1.83. Yes. Yes. Is that good? Okay. Other questions while we're here? Does the answer make sense? Yeah, question.
Can you go over how you got the 0.1604?
The 1604, yes. So what I did to get 0.1604 is I took E to the negative 1.83. I raised negative 1.83, and I got, you know where this comes from?
Yes.
Okay, so E is the number 2.71, so if you had a y to the x, you could do that, but you don't want to do that, you want to use the E key. If you have an e to the x key, you are either going to put this number in and then hit e to the x, or you're going to hit e to the x, and then you're going to put this number in. It's different calculators do it different ways. Yes?
I separated my ln fraction into subtraction, and
Sure.
I got a slightly different number. I got 1,427.
Sure.
Could that still be a rounding thing, or was that because I?
That's a rounding thing.
Okay.
So you rounded someplace differently,
Okay.
probably.
But that isn't because I did it slightly different.
You can do it, it should, both of those methods should come to the exact same answer if rounding is done the same way.
Got it. Okay.
That there's no difference between the two.
Okay.
They're mathematically equivalent.
So it isn't like I'm doing
Nope.
algebra wrong. It's
Nope.
just rounding.
Nope. And there are multiple ways to solve this, so it's always good to show you that. Other questions? Yes. Yes. You always get the equations. You always have all the constants. And if you think you don't have them, you should always ask. Okay. So I was going to say, was this a reasonable answer? Let's go ahead and write the answer here next to our starting conditions. So we had what? It was 14 something? 1426? Okay, great. By the way, a note on significant figures here. It's torr, not. I just care that I'm going to remind you that I just care that you're close on significant figures. Give me all the numbers on your calculator. I'll dock you for significant figures. If you give me one digit, unless the problem warrants one digit, I'm going to dock you points for significant figures, but just kind of be close. All right. Surely you understand that there are significant figures exist. That's really what I'm looking for there. I want you focused on the concepts and the algebra we're doing, not on did I get my sig figs right. All right, so is this a reasonable answer though? We started out with 300 degrees and we had a pressure of 228, right? Torr. Then we did what happened to the temperature? It increased. And what happened to the pressure? If I increase the temperature, should the pressure go up? Okay, so the answer makes sense. Other questions? Okay. We're going to move on then to a new topic. We're going to start talking about kind of this part of the chapter is called classifying solids. And it's going to be mostly descriptive. We're going to have some nice, fun reasoning stuff here at the beginning. But we're going to be classifying solids here into various groups and talk about their properties. So the first thing we're going to talk about is we're going to talk about ionic solids. So ionic solids, can everybody see that or should I make it bigger? It's okay or bigger? Okay. So ionic solids, or I should say ions form, let's start that differently. Let's say ions form crystal lattices. Okay, so that's like this picture we see right down here. We end up with this very ordered lattice where the ions come together. Why do they come together?
Because they're attracted.
Yeah, the opposite charges attract to each other. So ions form crystal lattices. They are held together by what we call lattice energy. Okay, which is the attraction between those charges. And lattice energy is defined as the energy required to pull them apart. All right, the lattice energy is pretty high for ionic solids. So they have high melting points. Okay, so how high these melting points are depends on two things. So the greater the charge is, the more attraction you have. This is actually, we're both related to, remember we have Coulomb's law? Coulomb's law tells us the force of attraction between two ions. So we have some constant out here. I can't remember what symbol it gets. I'm just going to call it a C. And then we have a, you want to help? You got it memorized? Yeah, we have Q1 over Q2. Do you remember what the constant, is it E? What? Is it a K? Thank you. So I'll just put a K out here, and then it's over R. Is it R squared? Okay. So for Coulomb's law, what we've got here then is our force of attraction. If we make these charges bigger, Q1 and Q2 are the charges, what happens to our force? It goes up, right? And then what if we take the distance here? What if we make the distance smaller? This number on the bottom smaller. Force also goes up. Does that make sense? To make this smaller? If making it smaller doesn't work, making it bigger certainly makes this smaller, right? We do the opposite. So the force of attraction between two ions increases with increasing charge. And increases with decreasing distance between the ions. Okay, and when we talk about this, we're going to talk about the ion centers. Okay, because if I have two oppositely charged ions, they're going to all touch, right? But it's what's the center to center distance is what matters. That's what goes into our R squared there. Does that make sense? Okay. So let's go ahead and use that. Actually, before we do that, let's remind ourselves how we can use the periodic table to tell us how big things are. All right, we know what charge. I'm hoping you can remember how to read the charges off the periodic table. What you may not remember is your trends for size so well. So here's our periodic table. Our ions get smaller as we do what on the periodic table? Okay, go to the right and up. Okay, so as we go over to the right, things get smaller, which is a little counterintuitive, right? You're adding more electrons. But those electrons, if you remember, see a higher effective nuclear charge as we go to the right. And so they're pulled in more. Okay, so the ions get smaller. So ions get smaller as we go this way, and they get smaller as we go up, because we have fewer shells, right? We add shells as we go down, each added shell is bigger than the previous one. So size is going to decrease in this direction. Okay, questions? All right, so let's now look at this table right here. Explain, see if you think of, everybody take a minute and think about why is, if I look at these two right here, the melting point of sodium chloride is higher, meaning it takes more energy to pull them apart, than the melting point for potassium chloride. Take a minute, look at that, and then I'll ask somebody to give me an explanation. All right, somebody want to give me an explanation for that? Go ahead.
It has to do with the fact that potassium has a larger radius than sodium, and so there's a much further distance between the chloride ions, between the potassium than there are between the sodium and the chloride.
Mhm.
So the increased distance decreases the force, and therefore it's going to be easier for those molecules to spread out and change phases, so the melting point ends up being lower.
Right. So that's a great explanation. The only thing I take issue with is the spread out, because the solid has about the same volume as solids and liquids have about the same volume. Okay. But other than that, great. So what we've got is the melting point of sodium chloride is higher than that of potassium chloride because the sodium is smaller than the potassium. Okay, they're ions in this case, but smaller than the potassium. Okay, and thus the distance between the atom centers is smaller. Okay, so when we think about Coulomb's law here, this is smaller, right? So force is bigger. So the melting point is higher. So if I was to draw these, it would look like this. I would have two chlorides, let's say. There's a chloride, they're the same size, pretend they're the same size, okay? And then my sodium would look, if I exaggerate it, my sodium would look like this, and my potassium would look like this. Well, actually, maybe that's not even very exaggerated, okay? And so the center to center distance here is bigger than here, so the force of attraction is lower. Does that make sense? All right, so we had one step down the periodic table there for distances. What about comparing these two? Magnesium chloride and calcium oxide. I want you to look at that one and just think about it briefly. You're almost out of time. This is awful. Think about it. Take a minute and think about it. I'll call it somebody else.
I just
Would
would the chloride be smaller than both potassium and sodium? Because it has a smaller radius because it's further to the right, and Na and Cl are on the same line.
No. So think about the other question. Well, the question is, would the chloride be smaller than the sodium and the potassium, right? The sodium loses an electron, right? So it has the electron configuration of neon compared to chloride, which has electron configuration of argon.
Okay, that makes sense.
Okay, and then for for sodium and for potassium and chloride, I maybe should have made the potassium a little larger. They're both here, okay? In terms of number of electrons, but potassium has more protons. Good question. All right, does anybody have an observation here? What do you think's going on here? Go ahead.
Doesn't it have to do like the charges because calcium and oxygen are both like +2, -2,
Uh-huh.
and magnesium is +2 and chloride is -1.
Yeah, so,
Something there, but I don't.
right, so it's the charges, okay? So remember, it's charges or distances. Let's take a look at these real quick. I want to make sure that I get this written down before we head out here. But, so it's magnesium chloride, right? So we got magnesium, we're going to compare for sizes, we're going to compare magnesium and chloride versus sulfur, right? Sulfide?
Oxygen.
I think these are very different. This is smaller, but not much different. Okay, these are about the same size. Over here we have magnesium, we have calcium. Calcium is bigger, right, than the magnesium. So we actually we have magnesium. We have some smaller. Both of these are smaller. Both of these are. This is a little bigger. This is a lot bigger. And yet calcium sulfide has or calcium oxide. Whoops. I should have. You guys got to keep me honest here. It's calcium oxide. All right, so let's try that again. So bigger here, right, for the calcium, but smaller for the oxygen. That makes sense? And smaller for the magnesium, but bigger for the chloride. All right. So we have a bigger and smaller. It doesn't seem like the size is all that different. We're not sure what to do with it. But what we do have is we have calcium has a +2 and oxygen has a -2 compared to magnesium's +2 and chloride's -1. Does that make sense? So more bigger charges. Yes.
Would you need to do more calculations if the size different was bigger and the
If you had both competing, you might have to do calculations, but I want to point something out here. That let's go ahead and take this table from your book, okay? And then let's look at sodium and potassium. Let's compare these two, okay? Which one's bigger, sodium or calcium? Calcium, by a fair amount, right? It's down one. What's bigger, chloride or sulfide? They're about the same, right? Chloride's a little smaller. This is a little, so we got bigger down here, right? For charges, +1, +2, -1, -2. Look at the difference in melting points. So when it's close or you're not exactly sure here, what's going to win? Size or charge? Charge. You could explain 90% of chemistry using charges. Okay? So charge is going to win here. If I give you this as a problem, and I really like these problems because they involve reasoning and using your trends and all sorts of stuff, that's a hint. So I really like those problems. I'm going to give you something that's obvious. I'm not going to have things mixing much at all. If that makes sense. Okay? All right, let's see. We've got 2 minutes left for me to actually write this out. I know you guys are just itching to get out of here. You were looking forward to your snow day, right, on Monday? We'll see what happens. Did you guys, I was told that I was just overreacting with the note. Did you take the note as the world is ending, stock up on food? Yes.
I got stuff.
Okay, so the chart said,
Okay, we got an extra chemistry question, not me being snarky.
oh,
Go ahead.
sorry, yeah.
No, go.
The chart asked about, talked about melting points, but wouldn't
Yeah.
the bigger molecule take longer?
Would a bigger molecule take longer to melt?
Does that make sense?
It's not a,
Does that correlate?
it doesn't correlate.
Okay.
So they're all really small and
Okay.
That's a great question though. A way to think about it is if it was a really big molecule, like let's say a fat. You make a really big molecule, you get lots of interactions. This is what we have. It's like what you're thinking about. You think about mineral oil, which doesn't have like minerals in it. Mineral oil has a high boiling point and also a high melting temperature relative to what it is, because you have lots of London forces. That's what's going on there. All right, I will write the thing down here and we'll call it there. You guys have a great weekend, and I grew up in Minnesota. I expect I should see you on Monday, but I bet it doesn't happen. We'll
Do you
see.
think we're gonna get all this done?